Okay. Oh, I can hear myself from your computer. Okay. So in this class, is this big enough? Yep. In this class, we're going to start talk. Okay, not big enough. Let's make it bigger. Good? Okay. So in this class, we're going to talk about Guardian. Guardian is a compiled, statically typed programming language, which is designed for parallel computing with guards. And hopefully, if you've used another imperative class-based language like Java or C++, which your homeworks have been in Java, so that should be familiar to you. A lot of aspects of Guardian should be pretty familiar. So first, we're going to look at ways in which it is similar to these languages. It's compiled, meaning it is translated from Guardian code into native code, which lets it run faster than interpreted languages. It's statically typed like Java, where you have to write types in your code. It's class-based like Java, meaning that all your code is going to be organized into classes, methods of classes. And it's high level, meaning you don't have to worry about memory management, undefined behavior, tracking pointers, or other things like that. So then we move on to the ways in which Guardian is different from some of these languages. So parallel safety is the primary concern because parallel programming is already too hard for mortals. Um, it's always asynchronous. We never block because blocking is a source of pain and incorrectness. We do not allow mutable state to have shared access. So if you have a mutable state, you can share it freely between different threads. But if you have mutable state, meaning state that can be edited, then that state can only be shared between threads if the compiler can prove that it's not accessed concurrently. So we have a type called guardvar that protects mutable state that would otherwise be unsafe to access. If you have a unique reference to mutable state, then you can move that reference between threads, which is still okay because only one thread at a time can access the mutable state. And we have this idea of every task being a linearizable asynchronous operation. We want to automate whenever possible. We've got garbage collection. We want to, whenever we can do some static memory management with unique references, a bit like Rust, to avoid garbage collecting unless we need to. And we have compile time assurances of progress and termination. So we try to prevent you from writing code where the termination condition of your program is ill-formed, right? Like if your program exits too early because it didn't wait for all the work to complete, or your program never exits because it's deadlocks, or it never exits because it doesn't properly check for completion of the work. Guardian tries to prevent you from writing those bugs. Uh, to implement this, we have a rule called the must consume rule, where if you have a future, you can't discard it. So if you have a function or you enqueue some asynchronous operation that returns a future, you have to make use of the future somehow or pass it along somewhere else. And the idea here is that eventually all of your progress will flow naturally to your main method. And then that way you avoid the situation where you have lost work or don't wait for all work to complete. Um, Parallel arrays are a primary concern because a lot of parallel code is based on doing stuff to big arrays or matrices of data. We prefer compile time errors to runtime errors. We want to minimize visual nesting, and we'd like simplicity, uniformity. All languages should strive to have these things, I think. Um, and we want to minimize or eliminate the use of atomics. So that's just a high level overview. You don't have to memorize every one of these bullet points. So that said, let's move on to Hello World. This is the obligatory first program you write in any programming language. Let's look at this a bit. Stop me from going too fast. So the first line is a namespace declaration. It's just like package in Java. You have to put your code into some namespace. It's just a way of organizing it. This organizes the code into modules. Next, we're going to have an import line. This works just like Java's import. We want to use this class out, and so we have to import it. Note, we have a double colon like in C++ when you're uh, writing the scope of a namespace, right? So like out println here, right? It's out double colon println because println is a static method, right? Dot is only for member function calls. It's it's like C++. Have you used C++? Any of you? Okay. Well, those of you who have used C++, this should be familiar to you. We have class hello. Instead of public or static or anything, we have a value. We'll talk about that later, but basically all classes in Guardian have a categorization that tells you how safe or unsafe it is to share that class between threads. So a value class in this case means there's no restriction on sharing it. We write fun for function, like in Rust, and we put the return type of functions behind them instead of in front of them, also like Rust. And println looks like this.
Should probably all try to run this.
Yeah, so if you have your account on the Flower server, you can make a new notebook like this. You can do from Flower, import, run, shift enter, and then you can type $% and then any code that you put in this cell will be run by Guardian. So it's flower.cct.lsu.edu, right? And when you sign in, you get this page. Then you just want to click new on the top right, and then notebook Python 3, and that will just kick you over here. Are we happy with this hello world code? Do we have any questions about that?
Can you copy paste it into the Discord so we can run it?
I'll do that and then. So it says entry function, that's all it just specifies name, basically. Okay.
Yeah, so if your function is designed to be the entry point of the program, you put entry on it.
And the entry function has to be named currently, right?
Currently, yeah.
If I wanted to import hello to a different file, I would do like import hello.
That's right. Yeah. So the namespace just tells you where the code lives, basically. So goo4 is the namespace under which all of the standard library stuff lives.
Three different types of classes.
Right now, there are three. You have value, vault, and unsafe, but I'll get to those in a bit.
Posted the code.
All right. Are we good to move on?
Yeah, I'll just give them a minute to see if people can get into them. Get them past that hurdle.
Go back to where it was. I don't think the statement.
Yeah. So you only need this once, just at the top of the notebook. If you run it once, you should be okay. This just enables the hack that we've done to allow Jupyter notebooks to run Guardian code.
So is Guardian like a language I can download just like Python?
It's not
a website.
Not currently, because it's still under heavy development. It's not finished yet. You guys are in some respect a bit of guinea pigs. You're gonna hopefully provide us with helpful feedback and critiques and such. And if you stumble in places where we don't expect you to stumble, then hopefully we can use that to make the language better. But for now, the way that you use Guardian is by using the notebook. What's the error say?
Anybody else have a problem?
So the from flower import thing has to be in its own cell.
You got it working?
I don't know what that means.
Yeah, so you see this gray rectangle? That's a cell. So yeah, hit shift enter. Right.
No,
Now you've got a new cell. Now you can regard word.
Has to be in a separate cell.
Because you've tried to run things 5 times. Just counts which iteration it is.
So just copy that.
There you go.
I think it's a little hard to hack.
Yeah, well, yeah.
Yeah, and then nice.
You know, this is a hack. We have a weird Python script that just calls the Guardian compiler.
I had a feeling.
Yeah. So Jupyter notebooks have this thing called magics where you can just define a function that you put $% and then the function's name, and then it passes the cell's contents as a string to that function, and then I just
Oh, I see.
Yeah.
The G run is literally like the compiler.
Yeah.
And
you can see the command right here. That's what's running in blue. And then here's the output from grun, and then here's the code itself, or the program's output itself.
how long have you been like developing Guardian?
This version of Guardian, maybe a year or so. Guardian in general, like forever, several years. This is version 4.
What was it compiled?
Right now it compiles to Java, but we also want to compile to C++ with HPX, which is a asynchronous runtime for C++. And then eventually LLVM, which is the big leagues. Are we good? Can we move on? Okay. So, right. So value in value class means that this class has either immutable state or no state at all, right? In this case, this class doesn't have any fields, so there's no memory attached to it, to instances of it rather. And the entry function just has a side effect. And so we can write value here. And that means if we wanted to send an instance of this class between different threads, we would have no restriction. Guardian would just let us do it. So let's start off with a very simple example. We're going to write a program that increments a counter from 0 to 100, and we're going to print the multiples of 100 to the console as we're doing that. So here is a version of that in serial. We have our namespace declaration, as we always must. We import out as we always will. We have a value class program. Here we have main. We're going to say let mutable counter equal 0. So we declare variables with let, right? In Java, you can use var to infer the type, or you can write the type name itself. But in Guardian, we always say let. And this will perform type inference. So we don't have to say what type counter is. The compiler knows what type it is, but we don't have to write it because it's obvious, right? 0 is an integer. And if we don't write mutable here, then we won't be able to change this variable. Then we have a for loop. We say I in 0 through 100. This syntax is not exclusive to for loops. This actually creates an iterator. So we're iterating over this ad hoc counter thing that we've created that goes from 0 to 100 exclusive. And then in that for loop, we're going to add 1 to counter. And we're going to check if counter mod 10 is 0. And if it is, then we just print out the value, right? Because we want the multiples of 10. And then at the end, we print done. Do we like this code? We understand every part of this code? Yeah.
Pretty much like iterators in Python.
Yeah, or in Java or anything else. You have a next method and then a has next method. You don't have to worry about the details of what an iterator is. Really, all you need to know is that if you want a for loop that goes from some number to some other number, then it looks like this.
What is it?
Yeah. I admire your curiosity. I just mean it's not required knowledge is all.
It'd be useful for a quiz.
Maybe it could.
I'm gonna paste the link to these pages into the.
Yeah, so these web pages are public. They're on the internet. So you can always copy the code from the pages themselves if you want to.
Yes, there's the link to the pages.
And if we wanted to write the type name of a variable, then it looks like this. We do a colon and then T, which is like Rust.
Screen there.
Oh, you
On the
can't.
flat.
Ooh, can I make that go lower? I sure can. Okay. Go all the way down then. Yeah, that's all the way down. Yeah. So if you write a type name anywhere except the function return type, use a colon like this. No, you usually don't have to. You usually only need to do that in fields because fields you always have to write the type. We use double colon to access static members. Parentheses in control flow, like if and for, is not required. If you put parentheses around this thing, it'll still work, but you don't have to. Yeah, we talked about this already. If you want the top bound of the iterator to be inclusive, then you put an equal sign here, right? You can think like, oh, the last value of this iterator will equal this value. So, okay, we can skip this. This is just telling you how the notebook server works. Do we all see this when we run that code? Those of us who ran it?
I can say, you go back to the start.
What do you mean?
This-
So you see how you have a new rectangle at the bottom there?
You can just keep stacking them on top.
Yeah,
of
you
each
can
other.
just keep writing code there. Each cell is its own program. So you can just have one big long notebook if you like. Or you can make new ones. right? So just to show that on screen, each one of these cells is its own self-contained program. You can just keep stacking them on. And it'll keep working. Okay. So you may have noticed that this code that we wrote, let me paste it in the notebook here.
You have to redo the work statement every time
No, just once.
and balance it.
Percent run at the top. So.
Yeah, the percent run thing you do need to do every time. So you may notice this code is serial, right? We're not doing anything in this code that runs anything in parallel.
Yeah.
So our objective now is to make this run in parallel. So the root of all parallelism in Guardian is the pool run method. This method takes a lambda. We all know what lambdas are, right? Takes a lambda and it will execute that lambda in parallel. Guardian uses a common thread pool for all of its parallelism. There's one pool that you submit every task to, and that pool will manage how the tasks are run. So when we call pool run, we're not necessarily spinning up a new thread. We're just enqueuing the task, and we trust that the pool will run it eventually. And in Guardian, we call any unit of work that we submit to the thread pool a task. So we want to count to 100. So let's say spin up 5 tasks, each of which will increment the counter 20 times. There's no practical reason to do this in a real program, but we're just starting simple. So here's a naive interpretation of that. This won't compile, actually, but let's look at it. So we have our mutable counter 0 again. We have our for loop 0 to 5 because we want to spin up 5 tasks, remember. We have pool run, and this syntax here, where we have a block after it, this is just saying that this is all a lambda, and we're passing it as the final parameter to this function. Are we good on that?
It's better to ask. But is there anybody who's having trouble? Even the way to ask.
Yeah. Does anyone have trouble with that notion?
Notion. The parameter follows the closing parentheses block.
Yeah, so this is just a lambda, right? You can imagine there's an arrow and then, Java style parentheses in front of it. And you just pretend that it's inside these parentheses. It's the final argument to this function call. But if you putting it after it like this just allows us to have a cleaner syntax, right? One of the problems you may have noticed in the heat equation when we did that with guards in Java is that we had a bunch of stuff encased in all of these curly braces and parentheses, and we have all this nesting, and we infinitely go to the right of the page. One of Guardian's goals is preventing that such nastiness. So inside of this, so yeah. Then you just write them in like normal, right? So like println here, this string is a normal argument. No, that only works for lambdas. So the intent here, you can kind of imagine, it looks like an if statement, right? You have, or a for loop, right? You have the control flow and then the code that runs. Here you have the thing that you're doing with the code and then the code that runs.
Like a verb object type of.
Sorry?
Feels like a verb object, like in English.
Yeah, a little bit. That's a good point. Right, so everything inside of these curly braces that we pass to pool run is going to be a task that runs in parallel. So each of those tasks is going to have a for loop that goes from 0 to 20, and it's going to, each of those 20 times, it's going to increment the counter by 1, and then do the same if the counter mod 10 to 0, print the counter out thing from before. And let's try and run that and see what happens to us. You may have noticed that this code has bugs in it. And indeed, Guardian catches us and it says, no, I'm not going to compile this. We can't capture counter on line 13 right here because it's mutable, right? So what do we mean by capture? So when we pass this lambda to pool run, we are referencing a variable that was declared outside of the lambda, right? Is that clear to see? And this is the same concept as in Java or any other language with lambdas. When you do that, what you're doing is creating what's called a closure, which is just a lambda with state that it captures from its environment. So when we write this lambda in the code, it knows that it's using counter, and so it looks for a variable called counter and saves a reference to it. That way, even if the variable goes out of scope, the lambda still can access it. And that's normal. That's how lambdas work in every language. So, okay, which part, did anything I say make sense?
Oh. Talking about scope, it made sense.
Okay, so this is a lambda that we're passing to pool run. And because it's a lambda, it's not running right now. It's going to run it sometime in the future. But even though it's running in the future, it's referencing a variable that we've declared here, right? And so the variable is not declared in the same place that all this code is, right? They're in different scopes, meaning that normally we wouldn't expect the lambda to be able to access this thing. But it does have the ability to access this thing because it saves a reference to it implicitly. The compiler does it for you. That's called capturing, because it saves it and holds on to it, so that way when the lambda runs, it knows what counter is. Does that help? Yep.
So I get that.
Yep.
I heard about something called binding. Is this like binding? At least for counter, the variable bit.
So counter itself is a variable binding, right? So binding just means you're giving a name to some quantity. So here we're saying that the variable counter is bound to the quantity 0. And the equal sign operator that we see in these languages means that we're changing the binding, right? Whatever counter was bound to before, we're taking that, adding 1 to it, and then rebinding counter to point to that new value. So capturing, you can imagine it's capturing a reference to the binding itself. Well, because that's the next step of this of this exercise, is that we want to be able to stop you from sharing memory between threads unsafely. And in Guardian, all parallelism is controlled by pool run. And the only way to give code to pool run is to put it in a lambda. And we have this concept of any code that's in a lambda might run at a time that isn't now. It might run in parallel in a different thread. It might run in the same thread, but asynchronously. It might not run at all. And so we have this notion of a temporal scope, which is a big word. Don't worry about it. But the idea is that this code is running at a different time. It is removed in time from when the code around it is running. And so the rule that we have, it says that if you have mutable state, then you can't capture it in a lambda, because that would allow multiple threads to mutate that mutable state unsafely. Do we like that? Does anyone not like that? Okay. Oop. So I already talked about this, but okay. Well, the first thing we'll do before we fix this bug that we have is we'll talk a bit about unbounded suffix lambdas. So this syntax here, where we put the lambda after the function parentheses instead of inside of it, we just call that a suffix lambda because it's a lambda that goes after the function call. This is one form of it called the bounded form, which is just enclosed in curly braces like you would expect. We also have a different syntax for it. So you'll notice how nested this is. Earlier, I mentioned that we wanted to get rid of this sideways nesting, or as we like to call it, the sideways pyramid of doom. Right? Because if you turn your head 90 degrees, it's like a triangle. One of the things that we've done to help alleviate this is we have the unbounded suffix lambda. So you can instead write this code here this way. So we've lost one level of indentation, and instead of putting the body of the lambda in curly braces, we just write it after the function call. This colon signifies that everything in this indentation level after this statement is part of the lambda. So we're just saying everything after this is run asynchronously. Do we like that?
So. There's like Python where the indentation matters now.
So no, the indentation doesn't actually matter. I said that to make it more clear. It's everything.
Within the scope.
Yes.
Okay.
Everything following this until the end of the enclosing scope. Right? So the enclosing scope would be this for loop. So everything up until the end of the for loop. Pyramids are nice, but with futures and continuation-based programming, you can get some really nasty pyramids. I mean, like off the page, 2,000 column long pyramids. All right. So do we all?
The general observation is the more indentation you have, the harder it is to read the code. And this way, we're trying to say, hey, it's really, you can really think of it as linear, because one thing after another.
I was just joking.
Yeah, okay.
Yeah, because like with futures, right? If you want to schedule something to run after something else, that something that runs after has to be indented. And so if you have 1, 2, 3, 4, it's going to be a staircase of tasks for no real reason. Right. And so now we're talking about the capture rules. Sorry? Okay. The capture rules, right? We can't capture counter because it's mutable. So how do we fix that problem? And of course, note that int is a value type, but the binding is mutable. And because the binding is mutable, we can't capture it. If it were just a regular non-mutable int, then we could capture it, but we couldn't assign to it. It's not mutable. It's read only. But this is read and write. So what do we do? Well, we have this type called guard_var, and this is just a type that encloses a value and protects access to it with a guard. So here we're going to say let counter equal new guard_var of int. We put 0 inside of it. Now we have a integer behind a guard. And guard_var is a vault type, which means that we can capture it between threads. And this binding counter is not mutable because the binding itself is always going to point to the same guard_var object. It's the guard_var object itself that manages the mutable memory. And so to access the guard_var, we call run guarded, remember? And that looks like this in Guardian. We pass the guard_var that we want to run guarded with to run guarded. And this pipe syntax, this is just the lambda's parameters. So previously with these suffix lambdas, they haven't had any parameters, so you haven't seen that syntax, right? The lambda to pull.run just takes nothing. But the lambda that we pass to run guarded takes the value stored in the run guarded. Well, actually, it's var of that value. Yes.
Is that pipe syntax a thing in other languages? I've never seen.
A few other languages do it. Rust does something similar. Some of the syntax is inspired by Rust, you might notice if you use Rust. Yeah. Right. So when you call run guarded on a guard_var, the lambda parameter is of type var. It's just a wrapper around the value. The reason it's like that is because Java just has, you don't have enough control over what's a reference and what's a value in Java. And so it's just an implementation detail. In C++, this would be more like a reference instead of a var. One plan I have to improve the language is to make the var thing more transparent, so you don't have to call get and set. You can just assign to it, but we're not there yet. Right, so basically the fact that the lambda takes a var, right? If you have a guard_var int, this parameter is var int, and var is just a wrapper that has get and set. And it's just an implementation detail because Java doesn't give you as much control as we need to have over what's a value and what's a reference. But it's something that we want to work on in future versions of the language. We're just not there at that point.
Takes what's inside the guard and stored in the counter.
Well, this is a reference to it, right? So normally we can't touch what's inside the guard var because we have to go through the guard. And what run guarded is doing is enqueuing a task that when the value is ready, we'll take a reference to it and then do whatever to it. So this is just like run guarded works in plain Java, just the syntax is different. And so we set the value to the value +1, and then we do the same logic here. Does anyone have questions about this? Okay. So, oh yeah, also a quick detail. Guardian lets you shadow the names of variables, meaning that even though we called this thing counter, we can call the parameter counter as well. Java wouldn't let you do that. It would say, no, you need to rename the variable. But if you do that in practice with run guarded, you end up having like, the same name, but with underscores or ones or something to distinguish it. So Guardian just lets you redeclare the variable, right? So the idea is after this run guarded and this colon, it looks like you're just using the guard var like a normal type because it's still called counter. So you can imagine this like counter.lock. And just like with lock code, everything that you do with the lock that you have is in the same scope and same indentation level. So even though we're not using locks at all and we're actually using guards with asynchronous tasks, it kind of looks like lock code, which is to say it looks simpler and more linear and easier to read. Hopefully, that's the goal anyway. Right, let's run that, or try to. Spoiler alert, this also doesn't work. So this error message tells us the future returned by the call to run guarded is discarded. Hint, you may want to pass this future to a function, call then, or assign with let. So the reason it doesn't let us do this is because we are ignoring the result of run guarded. And if you read the code through, it actually makes sense. Because what are we doing? We have a for loop, and so 5 times we enqueue a task, and then we print done, and then we return from the main function. We don't actually wait for the tasks to finish. If we were using locks, you would expect well, rather, if you're using futures in Java, you would expect a dot join here somewhere. But we don't have anything like that. And so Guardian rightfully says, hey, you're not waiting on this future. The program, if I ran it like this, would terminate too early. Do we like that? Does anyone not like that? What's your question? Yeah. So we have support for Java as well as Guardian and Flower, which is not in this class, but your homeworks are going to be in Guardian and you must use Guardian. Yeah, the Guardian homeworks will be explicitly, you must use Guardian for this.
This week's homework is Java. I mean, you could, unless you want to translate it to C++.
I don't.
Right. So this is the must consume rule catching us. So how do we make the compiler happy? So let's talk about latches. So we want our program to wait for the completion of a finite number of tasks, remember, because we spin up 5 tasks. Each of those 5 tasks does 20 things. And once all those things are done, then we can terminate the program. So we have a type called countdown latch. This is a thread-safe vault data structure. Vault is the type of class, meaning that there's mutable state, but it's protected from concurrent access. So we're allowed to share it even though there's mutable state. Countdown latch is one such class because it holds a counter inside of it, which is mutable state, but it lets you mutate it safely. So we're initially going to set this counter to the number of tasks that we want to wait for, and then each time one of those tasks completes, we decrement the counter by 1. And then once that counter reaches 0, we have a future which is completed. So when we want to wait on all the tasks to complete, we can wait on that future. And because it's a future, we can schedule tasks to be executed after that condition is met. So here's the same code from before, now with countdown latch. So we see we've added outer latch equals a new countdown latch with 5 because we have 5 tasks here. And then inside the pool run, we have an inner latch set to 20 because we have 20 operations per task here. And then after each iteration of the for loop, we signal the inner latch. And then at the end of this for loop, still in the task, we call get fut on the inner latch, and then we call .then to wait on it. And we have a continuation with colon. And then when this future completes, we want to signal the outer latch, which counts how many times this thing has completed. And then
Signal just count how many times something happened.
so signal on countdown latch means the counter is decremented by 1, right? So it starts at this value. Each call to signal subtracts 1. And once that counter is 0, then this future completes. And then at the end here, we want to wait on the outer latch because we want to wait for all of these things to finish. So once we wait on that, we call then, we print done, and then this whole thing gets returned. And why are we returning from main? So there's this thing we can do where we don't want to let you block. So we don't want you to be able to call join, even though that's what you would normally do here. So instead, if you return a future from main, then the program will terminate once that future is complete. So we've changed the return type of main from void to fut void. And then the future that is completed after the outer latch completes is the thing that we return from main. There are a lot of different new things in this code, so I'd like to ask if everyone understands this code. Does anyone not like this code? Sure.
So is latch paired with signal kind of like a while loop with a finite number of steps?
It's most like a thread barrier, right? You know how many threads you're waiting for, and then once that number of threads have completed, then whatever's waiting on the barrier can continue. But we use futures because in Guardian, we use futures for everything. Yeah. Yes.
So. Looking at the code, I guess I'm kind of confused on how it could talk compilers into the accelerator waiting technology, because it doesn't seem like there's I don't see this is.
Well, you're not waiting on it in this code. The fact that you're not waiting on it is the problem.
Yeah, no, I'm talking about in the second.
Oh, and the second one, this one.
This one is correct.
Well, let's see. Okay, I'll get to you in a second. I want to answer this other question first. Yeah, this one works, and this one runs successfully.
Just not seeing any, like, I don't understand where run guard is being used.
Right, okay. Because we call signal. So the compiler can tell that in the lambda that we pass to run guarded, we're making progress inside the lambda itself. So actually, in this case, it exempts us from having to use this future because instead we're advancing a different future. Sorry, I guess we're getting ahead of ourselves, but that's how I can tell.
And we realize that this is kind of head burden at first, but we're hoping that it becomes head helping.
Yeah, don't worry, we're not going to blister through this. We have plenty of time to sit and stare at it and talk about it. This is just the first touch point.
Yeah, and don't let him just keep going ahead if you don't get what's currently being taught. Let's not move ahead of what we understand.
Yell questions at me until there are no questions left to yell.
More example.
You will. Yes. Line F. Right. So inner latch up here, we're saying that we want a future to be completed after 20 somethings have occurred. That something is calling signal on the latch.
Yeah.
So what don't you get? Line F. Okay. I can't read apparently. Line F is saying get the future controlled by the inner latch and then schedule a continuation to be run once that future is completed. So get fut just means get the future that we're waiting on. Dot then means run this thing afterwards. Right. So Java, there are several different flavors of then because Java has made some decisions in regards to its type system. So you have then accept, then apply, then compose, then this, that, and the other. In Guardian, almost all the time you can just write then. And if you want to return a value, then it just works. And if you don't, then it also just works. May I move on? Okay. Yep. Okay, so this program's a bit ugly and verbose as it is. You'll notice that we create two latches, each of which just has the same number in its counter as there are iterations of the loop. We don't really feel like writing a latch for every single loop that we write. That's very redundant. So instead, we have, remember the loop operations we talked about with plain guards? Those work in Guardian as well. So we have loop marching for and loop par for. These are going to work like a for loop, but the body of the loop is in a suffix lambda, and the overall thing returns a future that completes when every iteration of the loop body has run. So remember that par for runs all of the iterations of the loop at the same time, and marching for runs them one after the other. So now we've refactored the program to just use the methods in loop. So now we have loop par for instead of the outer for loop because we want all the tasks to run at the same time. And the inner loop is now a marching for because it actually doesn't matter because we're synchronizing on the guard var. So marching for and par for will both work. I just felt like using marching for so you could see it. In effect, we're running this body 20 times, one after the other. And then inside of unguarded, we are, or rather inside of the inner loop, we're doing the same thing we were doing before. We call unguarded, we get a reference to the counter, we increment it, we do our logic.
Same thing.
No, so par for will run all of the iterations at the same time. Marching for will run one iteration, and then once that one finishes, run the next one. And then when that one finishes, run the next one at a time. Yeah. But even though it's sequential, it's asynchronous. So it's not going to happen in the current thread. It's going to happen at some other time. Right? So, and the lambdas that we pass to these loop methods have to return a future because that's how the loop method knows that it's okay to move on to the next loop iteration or when to complete the future. So we stick yield in front of these things that return futures. And this is going to get around the must consume rule, right? We're using the futures by returning them. And why yield instead of return? That'll be more obvious later, but basically when you're inside a lambda and you want to return from the lambda, you have to write yield instead of return. And without getting ahead of myself, the reason to do that is because if we don't have that distinction, if we just have return everywhere, then there can be situations where stuff becomes unclear and it's not obvious what you're actually doing, where you're returning from. Do we like this code? Yes.
Find the dot then line D.
Yeah, so we're saying when all 5 of the tasks that we've given to par 4 have completed, then print done.
Oh,
And then we return that because we want to return a future from main.
About then just kind of, you're done, just move on.
Well, dot then means after this future on the left is completed, do what's on the right.
Yeah.
or do what's below. See, because this colon means that this is a lambda that we're passing to them. Any more questions?
Okay, so I'm pretty sure I get what this does, like parallel 4, that's bar 4, 0 to 5, exclusive, so it's 5 times. I guess it assigns the variable I, but it has like some special thing that,
Oh, yes. Sorry. Yes. So the lambdas that you pass to par4 and marching for take an integer to just tell you what loop iteration it is. It's like 4i equals 0, I da da da, right? This is the I.
so
In-
it's the argument to the lambda.
Yes.
So it's like in like.
So in Java,
Have like the parentheses and then it's the actual lambda. This one is like.
Yes.
It's a bar group.
yes.
Okay.
All right, so instead of parentheses, variable, arrow, lambda, it's just bar and then lambda.
And so since it's lambda and since it's being processed inside this par 4, there needs to be a task that's given to the par 4. So that's why we're doing the future thing. which
Yes.
has a yield and all that.
Yeah.
And then it just so happens that futures can also assign more futures. So that one will also have a lambda inside, which is assigning. Well, it's not assigning. It's
So this is a task. And one of the things that this task does is pass a task to something else.
so. Is it for like all five of the par 4s have to finish before the event goes to?
Before
Yeah,
this then, yeah.
because it said done. It has to be done.
Well, right, but so par4 and marching for both return futures, and those futures are completed when those methods are done doing stuff. Right. Yeah. So this returns a future, but we're yielding it from the lambda from the task that we give to par4. So the lambda that we pass to par4 has to return a future because par4 needs to know when each iteration is done. And that iteration might be doing stuff asynchronously. Does that make sense? Well, what part does not make sense? I'm going to explain more, but I want you to understand that first. Sorry? Okay.
I don't know. I guess the yield part is kind of confusing.
So we agree that we need to return a future from this thing somewhere.
Right.
Yeah. Marching 4 returns a future itself. So we want to say the future that marching 4 returns is going to be what we return, or see, return is overloaded now, so that's why we use yield. We want to yield something from this lambda, and the thing that we want to yield is this, and so we just write yield there. Does that help?
Kind of.
In which way doesn't it help? Okay, think of it this way. We want to be able to say concretely when one iteration of this is done. And the way that we do that is by returning futures. When is this loop body done? Well, once we've incremented the counter 20 times. So this future represents the counter has been incremented 20 times because this is a loop that runs 20 times and all it does is increment the counter. Because that's how we pass futures around. Right? So lambdas have argument types and a return type, just like functions. Does that make sense? So whatever function or lambda that par4 receives has to return a future that says this iteration is done. And so yielding a future says that this loop iteration is done whenever this future is done. Do we like that? Can I move on? Do we want to stare at this a bit longer?
Something about it, maybe like the verbiage as well. It's kind of unfamiliar.
That's fair enough. Well, a future is a common thing. You may have also heard promise.
No, I don't have a problem with that. Because it's not natural.
Right.
But okay.
The goal of all this future stuff is that every part of the code knows when it's done. It knows when it can run, what has to happen before it can run. And yield is just saying that I'm not adding any additional logic in that respect. I'm just saying when this thing is done, this other thing is also done. Okay, for time's sake, I'm going to move on. But if you have more questions later, please yell them at me. Right, and did I run this yet? I did not run it. Let's run it. So for the sake of example, let me take the yield off of this and run it that way. Didn't like that at all. It disliked that more than I thought it would. Oh, here we go. Right, so if we take the yield off, then now we have a future that is returned by marching 4 that we're not doing anything with. We have to do something with it. And in this case, the thing that we're doing is just passing it upwards along to par 4.
Doesn't return anything until like the very end.
Yield means return, except we're returning from a lambda instead of returning from a named function declared with fun. That's the only difference. It's like return in Java. If you write return inside of a lambda, it's like yield in Guardian.
It's getting more confused on these things.
Is the word yield confusing? What if I write it like this? Does that make more sense? Okay, well,
Say, the. Yeah, lambda is just.
it's just a function with no name. That's all it is.
Like the part on the right side of return as it stands now, the whole like, it's like an expression.
Yeah,
Expression
okay,
Sort of like evaluates to a future.
right.
And then when you do dot then on it, you expect by then the future will be completed. You can work with whatever the future did.
Right. So maybe it makes more sense. This is all one expression. So normally in a function, we would write return and then some expression like return 5, right? This is just one big long expression because remember, this is all one function call. The lambda is to the right of the function visually, but this is all one function call. This whole thing returns one future. And then we're just saying that future that we have, return it again. That's all it is. I'm glad.
Future and like, you like writing like 5 somewhere to tell it, it's like, what is this?
So how about this?
But it's not 5, like return or +5. You at least, you don't know if it's necessarily getting used right at that instant, but the problem with this.
Does that help a little bit? Now we're assigning this future to a variable and then returning the variable. These are equivalent, but maybe this makes it a little more clear what's happening.
So to clarify, a
Yeah.
lambda doesn't have to be a feature in this. It's just the lambda's passed to it to create it.
It just so happens that par 4, marching 4, run guarded are functions which take lambdas and also happen to return futures. Lambdas don't have to return futures, but in Guardian they often do. Because a lambda is usually a task, and a task tends to return a future.
There's always basically this like lambda definition, bracket, statements, yield.
I'm not sure what you mean.
Oh, by like the syntax. Is it always in a yield or a return or either?
It doesn't have to be. Well, you see what I've done here is instead of returning it directly, I'm just assigning this future to a variable and then yielding the variable. But I could instead of yielding it, I could do then, right? I don't have to yield it.
I asked a question I know. There's no return or yield inside of the lambda that begins at C, so I think.
Right.
that really makes sense.
So
The lambda can also be void.
yes, a lambda can be void. And the one that we're passing to run guarded in particular is void. Yeah. Lambdas are just functions. That's all they are. They're functions that don't have names. Any more questions? Do we like this code now? Who doesn't like this code? Everyone loves it. Great. Okay. This is all what I said. Okay, so in asynchronous programming, there's a very common pattern where you have a function that's going to perform some asynchronous work, and then it's going to return a future representing the completion of that work. And so very commonly you have a function. This happened in the heat equation. We have a function, we say var future equals new future, do a bunch of stuff, return the future, and then somewhere in the bunch of stuff, we have a future.complete. And so one of the features of Guardian is designed to make it a little easier to write functions like that. And so we have the concept of an async function. And in an async function, you always return a future. And instead of being able to write return, you can write async return. And what async return will do is async functions implicitly construct a future at the beginning and return a future at the end. And async return completes that future. So it helps you. Another thing that async functions help you do is it lets you avoid having to write return, yield, yield, yield like this. Right. And so because we have the distinction between return and async return, that's why we've decided to invent the distinction between return and yield. Because if you're inside an async function inside of a lambda, then return might refer to the lambda or the function, whereas async return always refers to the function. And so you can have return and async return in the same place, but that they do different things, even though they both have the word return in them. And so because of that, we've split apart return into several different keywords. So return is when you're in a normal function. Async return is when you're in an async function. Yield is always when you're in a lambda. And if you're in a lambda, you can do async return, but that will affect the function all the way up. No matter how deeply nested you are, async return is always going to target the function. We have done and retry. These just mean yield false and yield true. This is for condition variables, which we haven't talked about yet. And then async done just does async return and done together. Excuse me, together. So in this case, it doesn't actually help us. It makes the code longer because this example is so simple. But here's what our counting code looks like with async functions. So now we have less nesting and less yield stuff going on. So in our main function, we create our counter. We do a par for loop from 0 to 5, and we yield this function call add to counter 20i. And then after this loop finishes, we print done and async return. And because this then is here, this code is inside of a lambda. But in spite of that, we can still do an async return that affects this function, which in Java would require you to have a future and do complete on it. But in Guardian, doing that can look like returning from a function. And visually, you are returning from the function. It's as if you're jumping all the way out of the Lambda stack and returning straight from the function. And now this add to counter thing, we've added a function here. This is just the inner loop where we have our marching for. It looks exactly the same as main. This is just going to do a marching for from 0 to n and increment the counter that many times. An increment counter is the unguarded code where we grab the guard for counter, we increment it, we print it if we need to, and then async return. Any questions about async functions? What is confusing you? Okay. Feel free to stare at it. Sometimes you just have to stare at these things. It's okay. Let me try and get more of it on screen at once.
Okay, so like, why are they separate now?
We just chose to separate them. This is just an example of how async functions work. This is just a different way of writing the same program.
Same order.
What do you mean?
So one's on the inside, we're gonna return first, and now they're like.
Well, they still are nested. It's just that now instead of having a bunch of lambdas, we've given the functions names and called them async function whatever instead of just having a lambda there. Right? So if you substitute in this block of code right here, and then substitute this block of code right here, then it's the same thing. Well, this is just how programming languages work. That's how function calls work.
What's terrible? Hard to look at.
I'm sorry.
What's hard to look at, what's terrible?
So like, you split them up instead of just keeping them nested.
Oh, well,
Well, like I said, for this particular program, it makes things worse, right? You wouldn't do that for this program, but I'm doing this because this is the simplest example we have, and I wanted to show you how async functions work. That's all.
sometimes you want to split things up just because they get too long.
Yeah, making it lost.
There are better examples of async functions a bit later, and hopefully it'll make more sense. This is just to expose you to them. Yep.
So we chose to define the function static in this case.
Yeah.
Okay, so it references the counter that's on main here.
Well, so we pass the guard var to the function. See if the function accepts the guard var.
Is it possible to avoid that, make it non-static, and then still use counter? Or do you need a static function that passes counter?
You could do it that way. We've just chosen not to. Yeah, I could have program be a class that you would have to instantiate, and then guard var could live in a field on that class. That's valid too. I just wanted to transform the program as little as possible to get from A to B, but
Then async function.
right. And because we're in a lambda here, so normally in Java, if we wrote return in this position, it would be returning from the lambda. But what we actually want to do is return from the function that we're inside of, because that function completing represents a task completing. And we just want to say, no matter how deeply nested in a lambda we are, we want to say, I'm done with one unit of work now. And even though in this particular example, it makes the code longer, it helps us avoid having these nested lambdas where we say return yield, 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 yield. Are we happy with this? Okay. Some languages with async functions have this function coloring behavior where if you have an async function in JavaScript, then any function that calls it has to also be async. Guardian doesn't have any of that. Async functions are just regular functions, except that in the body, async return is possible. That's all it is. So we're done with this page. Any questions about this page before we go on to the next page?
So I guess like in other programs, they only enable an async function that's inside of another async function. Why is it that we're able to get around that here? It's probably like a clear answer. I just can't think of it.
So async in those languages means something a bit different from what we're using it to mean. Usually in those languages, async refers to some kind of coroutine thing, which means that so you have two operations. You have async. Well, you have two concepts. You have async and await. And the idea is that you write your function, and every time there's an await, then you split the function into different pieces. And so await means suspend execution of this function until the part above or the thing that I'm waiting on is done, and then resume it. So those compile down to a state machine, and the state machine doesn't know what to do if you have an async function being called in a normal function, because those normal functions don't have the state machine generated. Does that make sense?
Sure. I feel like why would it generate a state machine in this case and not this one, and then this one could just be like much simpler, but I don't have to think about it, I can just think,
Yeah.
that function doesn't have a state machine, this one has a state machine, so when you have an async in there, it doesn't know what to do.
So
it
the
just
word-
doesn't really work out. This one's
Yeah.
a little different.
The word async in the two languages mean different things, right? We just chose the word async because it means asynchronous. But in those languages, it means we have coroutines and suspended execution that we can context switch and stuff. But in Guardian, it means we are able to return from that function inside nested lambdas. Any more questions? Okay. So next up, everyone's favorite problem, Fibonacci. We're going to make Fibonacci in Guardian. Fibonacci is defined like this. We all know what Fibonacci is, right? I don't have to define it for you. Okay. So here is a serial Fibonacci program. And are we all okay with this code? Do I have to explain anything of this code? Sorry?
You go so fast.
Well, that's fine. Tell me if I'm going too fast, tell me to shut up and let you read the code. Is everyone else good? Okay. So if we run it, we just see the Fibonacci numbers. So to parallelize it, I think you've already seen this stuff before. We run one of these two calls in a different thread and then wait on it and then return the result. Because we just say, every right child of this tree runs in some other thread. So let's add a function to this previous code called poolfib. This will create a future event, and then asynchronously, we're going to call fibn.then. So fibn doesn't return a future yet, pretend it does. We're going to wait for the result of this, and then once we have it, so now then takes a parameter because fibn returns a future of int instead of a future of void. So this is the int inside of the future. And we're saying complete this future with that, and then we return it. Guess what? This is what async function is designed for. So we can write this function like this instead. And we don't have to worry about doing this or completing the future. We just say asynchronously get the value of fibn and then return it. So if you're wondering what async function does, you can read these backwards. You can start with this, and then it compiles essentially to this. Are we happy?
Inside of your async function, define function called poolfib. It takes the argument in. This is what we normally pass to the Fibonacci function. However, if we want to run it to the pool, you basically provide as a lambda for the pool to run. And then it's just when the lambda completes, it just returns the result of the Fibonacci because it was dot then. And then I guess when they have a lambda define the bar in F is really the return of the fib event sequential.
That's right.
So the async return, since it's inside a lambda, doesn't care. It just goes straight to async pool fib.
That's right.
Since it's a future, it's a future because you're trying to do the async thing. You don't know when it will return. You just know that it will return. It's just async. So it's async return.
Yep. So now, of course, we have to go back and modify fib to make it return a future. So we slap async on it. We say it returns a future event. We check to see if n is less than 2. If it is, we just return it. Otherwise, we async return these two. So here's our program. There's a bug in this code. Can anyone find it? There's actually a few bugs in this code, at least two. Yeah. I'm sorry, I'm having trouble hearing you. That is exactly right. We just, F is just pointing to a future, and then we just print the future. We don't call then on it. So what we're going to see is a bunch of java.ling.completable future not complete, and then it's going to terminate. So we have to wait on these somehow. Can anyone find the other bug? I'll give you a hint. It's in this code.
There's no call.
Yeah, that's another problem. But there's okay, so there's three bugs in this code. The third one this year. What's wrong with it? Yeah, it's just like return, where you can either return nothing and have it be a void or return something. So that's fine. The problem is that fib returns a future. And so we're calling the plus operator on future int and future int, which doesn't make sense. Right? And then if we try to compile it, that's what Guardian will say. Hey, we're trying to add two futures. That doesn't make sense. So what we want to do now instead is in fib, we're going to call the two recursive calls and store them in two futures. We're going to do f1.then, f1, f2.then, f2. Now we have the two integer values instead of the two futures, and then we can add those together and return those. Guardian doesn't like this either because there's just a limitation of the compiler that this code should work. It just happens not to, but that's okay because we have a better way to do that anyway, which is the fut all function. So this is like, I don't know if you've seen it, but Java has completable future.all of, which takes a bunch of futures and returns one future that is complete when all of them are complete. So we do the same thing where we get our two futures from Fibonacci, and then we pass them to fut all as an array, and then do then. So this thing returns a new future. And so we're just saying when all of these futures are done, run this code. And fs, this is an array of results matching the array of futures here. So fs sub 0 and fs sub 1 are just the results of f1 and f2. And then we add those together and return those. And then finally, we just need to turn one of these fibs into pool fib. That way, this one is running in parallel, whereas this one is going to get kicked off by the current thread. And then everything together, here's just all of the functions that we wrote all in one program like this. It doesn't work still because we didn't fix that one bug where we're not waiting on the future. Normally, the must consume rule would have caught us, except that technically we did pass the future to a function. We passed it to println, and so there's a side effect. And so we can't rightly say that we haven't used the future, even though that's clearly not what we want. So, yeah.
That means the plus is defined.
No, we fixed that, right? So in fib, we are waiting on these futures and then adding them. But in main,
Yeah, it's converting to Java, and Java just defines, all methods have all objects have a two string on them, and plus is defined for string.
oh, down here I see, yes. Yeah, so plus on a string just stringifies everything. Sorry, I'm just misunderstood you.
I could have probably.
Nah, that's all right. So yeah, we see that. And then we just change that silliness to pool fib of I dot then, right? So we just call pool fib on whatever iteration number we want. We wait on the result, and now we have an integer, and we just print out the integer. Pretend you didn't read that. What's the bug in this code now?
So, I suggest you, the thing is, you didn't consume the future that Ben is out there.
You are correct.
Imagine me, yeah.
A very astute student.
But you would like to, if you want to try to arrange your coffee shop thing, perhaps.
Okay. So, are you gonna give them the first Guardian homework today or no? Okay. Well, so because these Guardian homeworks are a lot of new information and we want to give you the best chance possible of doing them, I think we're gonna give you more time than normal, right?
Yeah.
And also,
Fit somewhere.
so I had a professor a couple years ago who did something that I thought was genius, and he said, if you want to review for the midterm or the final or whatever it was, I'm going to be at Highland Coffees from this time to this time on this day. And if you want to come sit with me as a group and we can just informally review stuff and look at things. And there seems to be an anxiety among a lot of students of showing up to office hours because that's where all the big scary adults are. And right. So I thought if any of you guys are interested in something like that, we could meet at Highland Coffees at some point. And I could answer your questions about Guardian. This will be more relevant, I think, when the homeworks are given out and you're having to write Guardian code. But does that interest anyone?
I mean, it does. I don't know when.
Yeah, well, I guess part of the goal is to figure out what time works for everybody.
There isn't.
Well, one option is to do it just right after this class. Just okay, fair enough. Well, we don't have to figure it out right now because we don't have any Guardian homeworks out yet. So maybe over Discord we could.
Yeah. You
Coordinate.
just Times.
Yeah.
That-
When are you available?
Well, that's complicated. So I was hoping I could hear from you guys when you guys are available, and then I could see what works. Yeah, could be after 6. I don't know how late Highland Coffees is open. They're open pretty late, huh?
Takes me 45 minutes to get to that side of campus here when I get out.
By foot or by car?
By foot. I can't park on the side of campus because I live in West Campus. So
I
have
see.
West side registration,
Well,
which is
okay.
the stupidest thing they've ever done to campus parking.
There are plenty of stupid things done to campus parking. Do you not anymore?
They have West and East.
Oh, I see.
I live in West Campus, so I have a West one. All of my classes are on the east side of campus, so I can't drive my car anymore.
Well, if it makes you feel any better, they got rid of about 1,000 commuter spaces to build a dorm room, and they are compensating for those 1,000 spaces by adding 200. You may notice that 1,000 minus 200 is still 800 missing spots, but
100%. Awesome. Campus house. Which.
will be.
Like, nobody can live in ECA anymore.
Because I guess the freshmen need to live somewhere, and the upperclassmen can go live somewhere else. We don't care. I don't know.
If you're out of state, you can't live in the state, which is what I have. So if I move to Louisiana, I lose $20,000,
Huh.
which is a bit more than an apartment.
Can you be homeless?
Theoretically, I just can't have my name on a lease anywhere down here.
Well, anyway, Highland Coffees closes at 10, so that's our upper bound. Do we prefer mornings, afternoons, evenings, weekdays? Sorry,
No,
not mornings.
most of my classes start at 9, and then I have class until 6.
Um,
And then it's spread out.
other days, well, so like 7 p.m. Yeah. Does anyone else like that?
All right.
Does anyone hate that? Okay, no one hates 7 p.m. That's a start. Tuesday and or Thursday? Ugh.
Wednesdays.
Monday? How about Monday or Wednesday?
Tuesday, and I can't do Thursday.
You have a class on Tuesday and when, you said? Okay.
And
You do Wednesday?
How about Wednesday? I should be able to.
Wednesday is great.
Wednesday at 7?
Wednesday at 7.
Okay. There seems to be consensus.
Oh, yeah, we should ask him.
Hopefully it works for him.
Does anyone hate Wednesday at 7? Okay, no one currently hates it.
I couldn't make any time, so it wouldn't matter.
Well,
It's here, I suppose.
no worries. And again, this is optional. It's not required or anything. I just thought if anyone wanted some additional study time or help or whatever. It may be the case that when you start writing Guardian code, you end up with bugs that are my fault instead of your fault because I wrote the compiler. So,
What more is there to do in this development of Guardian?
well, there are a few language transformations I want to add. Like, for example, there are times when you have futures of futures. I want to automatically handle those cases. There's a few other things that are not on the top of my head right now, but generally it's in a good shape. It's in good enough shape that I'm giving it to you guys. But we also need to work on more kinds of computations. Like we're not touching on divide and conquer algorithms in this little slice of Guardian because we're still figuring out how to make it good. That's one example. Do we have anything left in here?
Wait, so dot then there,
Right, we still have to wait on this future. Well, we still have to consume this future somehow. Because then, sorry?
said the old, I'm getting gone.
Well, well, no, that's right, actually. We want to turn this loop into a par four or a marching four, and then yield it from that loop. That's exactly what we do. We have a marching four, and then we just yield it from inside the marching four. Right. So we're telling the marching four one iteration of the loop is done after we've evaluated pool fib of I and printed it to the screen. And now, of course, marching four returns a future that we're not doing anything with, but we can just return it as well. We could also make main async and then do dot then async return. Those are equivalent. Yes.
Yes, we need those.
Yep. Well, I'm at the end anyway. You are released.
You know what that was?